Okay, radio astronomy. It's just another form of electromagnetic energy, like light, coming towards us. Okay, can't see it, but it's there. So this gives a kind of a overall, well, a very large view of the electromagnetic spectrum. And of course, we start out with AM radio, approximately 10 to the 3 meters in wavelength, and we move on to smaller and smaller wavelengths, and of course what that means is higher and higher frequency. Now this little area right here is the area that I spend most amateur radio astronomers look in, around 20 centimeters, right in this area here. Now, in physics, one of the things you learn is something called black body radiation. Any mass above absolute zero emits a signal. Your body emits a signal. That bottle of water emits a signal. Of course, they're all blended together, so we can't pick them out in this room. But this gives an example of how strong it is versus the curve. And if you get any 2 points of measurement at different wavelengths along these lines, by using, I guess, trig, you can determine the shape of the line and approximately the actual strength of this point, which you then can use to determine distance. Now, most of us, many of us in visual astronomy are familiar with spectroscopy. You look at certain things, you break it down in a spectroscope, and you can see that it has different lines, and that means it has different, the light is passing through different gases, okay? And that's because of absorption, okay? Hydrogen has a particular signature, so whenever people break these spectroscopy lines out, they can tell basically what gas the light had to pass through before it got to you. Gases also emit signals. Remember, gas is a mass, and it's above absolute zero, so it emits a frequency. And here's my favorite right up here, hydrogen, 1420.4. Okay, that's the magic number that we all know and love in amateur radio astronomy, 1420.4 or 21 centimeters. That's what we go looking for most of the time. So,
what's the protected on the right column?
Pardon me?
The right column?
I don't know.
Okay.
Sorry. I think it's possible that the FCC doesn't permit people to transmit in those areas, so that if astronomers are out looking, they won't get confused. I think.
Yeah,
I'm not positive. Okay? Now, let's see if this is going to work. It's supposed to. Okay. This shows you why hydrogen has a 21 centimeter or 1420.4 frequency. As the electron goes around the nucleus, it goes at a certain speed and it changes state as it's going around. And it does that at a specific frequency. Every element has its own frequency, and that's why they're all identifiable. This is interesting because it tells us why we can look where we want to look. Now, fortunately, the Earth is surrounded by an atmosphere. It's a good thing, right? Well, one of the reasons it's good is because it keeps radiation that we don't want from hitting us. All right? Now, this is the atmospheric opacity, or how much is blocked of what is coming in. And you can see for the most part, up until we get to the light range where we get sunlight, and infrared, which warms us, it's pretty much opaque. So nothing gets down. And then we have a dip where the various energies from the sun are allowed to keep us alive. And then we get some more peaks. And then we go into this area here, which is like the infrared. Well, at these frequencies, that's why we have to put up Hubble and other similar satellites, because once again, the atmosphere is opaque to those frequencies, and we have to go above the atmosphere if we want to do infrared imaging to find a lot of the stuff that's going on. Now then we get back down here and we see a big dip down here, and there's our little range there again, approximately 21 centimeters, where my favorite, excuse me, our favorite frequency comes through. And as you can see, down here we can use radio telescopes to image those things that can pass through in those bandwidths. If you have any questions, raise your hands. Okay, so what does the radio sky look like? You know, we all have a general idea of what the visual sky looks like. We see it in books, we see it in Kyle's images. I keep wanting to say Carl, I'm sorry. And guess what? The radio sky doesn't look that much different at certain frequencies. Okay? Now this happens to be at 408 megahertz. There's lots of different things. I don't know specifically. I didn't study why 408 is significant. But I want you to notice right up here. Okay? There's a little red dot up there. That means that it is an incredibly strong radio source. And it's at all frequencies. That is Cassiopeia A. It's the little remnant of a past supernova that's inside Cassiopeia. That is the strongest radio source in our sky. Okay? Of course, we have the Milky Way. Down here, there's a little dot, not quite as strong. That's Sagittarius A. That's basically the center of the Milky Way. Okay? So as we're looking through this, these are the kinds of things that we try to detect. So, supernova, remnant, Cassiopeia A. Again, the strongest radio source in our night sky. All frequencies. So, many other frequencies. We've got everything from 408, atomic hydrogen, molecular hydrogen, which basically, I'm not sure, let's see, what do they have? I believe it's molecular. This is the one that I look at because it's the 21 centimeter. But all different frequencies, you see slightly different things. So,
is this looking along the Milky Way plane?
Yes. Yes. Now, when you see those fancy images of the pillars of time, all they did was take multiple different frequencies of light and radio, change them into colors, and put them together. Those don't exist in visual light. They're not there. You can't see them. They only exist because of the science of overlaying images like this to get a complete picture of what is in that piece of sky. All right, so what do the professionals use? Well, we already saw some of that well, this is Arecibo. And by the way, Arecibo is back online after the hurricane, and it has just been taken over by University of Central Florida, leading a group that is now running it. So they have their own fundraising, and everything is going on, and we're really excited that they were able to keep this online. And then we have the VLA. The VLA is out, I think, in Arizona, and it's basically 27 dishes, okay? And by spacing them farther apart, they get something called interferometry, all right? By taking them and putting their signals together from two locations that are 100 meters apart, you get the effect of having a 100-meter dish. Okay? They can put these things like 30 meters apart. Excuse me, 10 kilometers apart. So they get a lot of coverage, a lot of very small bandwidth because of the relative large size of the interferometry that they use between the various receivers. And then, of course, there is the GBT. They call it the Green Bank Telescope. I call it the Great Big Telescope. Okay? And that's compared to something that we have in SARA, Society of Amateur Radio Astronomers, called the Itty Bitty Telescope, the IBT, which is basically a small TV dish that we use to demonstrate the function in the... We use it to demonstrate in STEM classes, school classes, and things like that, the concept of radio energy coming in. If you set it up right, you point it at the sun, you see a signal, you point it away, you get no signal. That's radio astronomy at its basic core. As they said, there's about 500 squares in here, each about the size of a king-size bed. Every one has a motor at each corner. There are over 2,000 motors tilting these things based on laser imaging and distance to get them within 1/10 of a centimeter of exactly the right location. Because if it's not perfect mirror, what do we know when mirrors aren't ground correctly? Who's here from the mirror lab? What happens? You don't get a good image. Well, there you go. Same thing here. They just are constantly grinding this thing all the time. When it gets hot, when the weather changes, if a bird goes doo-doo on it, we adjust. When they first built this about 15 years ago, after all the motors were installed, they had about 200 they bought as spares. Well, after about 10 years, they used up all the spares. Because they go bad about 2 a year. So they had to contract with a company to rebuild them. So now every time one goes bad, they have to send it out, have it rebuilt at a cost of many thousands of dollars because those motors have to work or the antenna is of no value. So, what does the amateur radio astronomy community do? We work with the professionals like optical community does? Yes, of course. There are many projects that we do in radio astronomy which we can send data in to be part of a larger database, to be combed through at another time. In what we call the super low frequency area, we have a system called SID, Sudden Ionospheric Disturbance Radio. We sell these kits for about $150. Once you put it together, it has to be tied to a PC. It runs all the time. And it's monitoring VLF or SLF signals that are coming in. There are many SLF transmitters around the world. In case you didn't know, submarines communicate with shore using SLF. So if you happen to be in the area where you can receive one of those signals, or even better if you don't, okay? Because what happens if there's if there is a sudden ionospheric disturbance, all of a sudden that signal will bounce places it doesn't normally. And if you pick it up, that means something happened to cause that signal to come back. And depending on what the frequency is, you record that, you send it in. Stanford University runs this database, and there are people all over the world and all over the country that are constantly running this program. And when they see a blip on their screen, they ship it up. Actually, I believe it's automatically uploaded to Stanford through a program you run on the PC. So they're constantly looking for these sudden ionospheric disturbances. Jupiter emits a signal. We sell a radio called Radio Jove. It's part of the Radio Jove program. You can detect signals around 25 megahertz coming from Jupiter. And there's also a signal that's emitted, something to do with the interaction between Io and Jupiter. We don't fully understand it, but sometimes the signals that are received help us understand so that they can get a better handle on when it happens, what the phases are, what the locations of Jupiter and Io are, things like that. FM meteor detection. We have people that can measure signals bounced off the ionized tails of meteors. So every time a meteor goes by, it's not just what we see blow up in the sky and get on channel 10, it's whether or not we can receive a signal bounced off the tail of it. UHF, let's see, what do we have here? Looking at supernova remnants, and of course here's my good old 1420 right here, and spectral scans in and around 1420. SHF, here's my IBT, the itty bitty radio telescope. Basically it's just good for STEM and educating in schools. It's not, we don't have the capacity, most people don't have the capacity to build receivers and antennas that can really go in and utilize this stuff. By the way, it's like anything else. How much does it cost? How much do you have? Okay? We'll take it all. There's the IBT. Basically, it's just a TV, direct TV antenna, and we put this little detector on here. All it is a signal strength meter. And when you point that at the sun, it's going to show some signal strength. Point it away, there's no signal strength. It shows that, yeah, we have directivity with our dish, and there is a signal somewhere in the 15 to 20 gigahertz range, because that's what these antennas are tuned for. Okay, why did I put this on here? AM radio transmitters, again, if any of you are into ham radio, you know that there are skip zones. And by studying those, we know where the various layers are, and we can determine the distances based on where the signals are received. This is the SuperSID radio, the one that detects the SLF frequencies. And we build a small antenna. You can put it in the roof of your house. You know, if you're so inclined. Basically, this just goes USB into a PC, and you have to leave it on all the time because you're constantly monitoring. All right. Sorry, I put this slide in here and I forgot what it's for. Solar radio, solar radio, solar radio. Sorry. All right, radio Jove. These are the kinds of things you're going to pick up. Now, again, if you're into amateur radio or any kind of radio, you know that you have a carrier at a certain frequency that has no information on it. All right? It's called a C1 signal. It's a carrier. There's no information on a carrier. All right? If there is information associated with that carrier, it's called modulation. Okay? One type of modulation can be turn it off and turn it on. At a given rate, that's called Morse code. Okay? That's called C1. C1, yeah. You can put amplitude modulation on it, and then you hear things like what you hear on your radio. If it turns on and then turns off at a certain rate, this is signals that you might receive from Jupiter. That's how we know we're getting a signal from Jupiter. Okay? Basically, it's just two big wire antennas crisscross, so we get total directivity. Now, obviously, Jupiter isn't in our sky all the time. It has to be when it is in our sky. So that's what we do with Radio Jove. And again, there's a group of people that collect all that data, put it in databases. Yes, sir?
Does that mean there's a ham radio operator on Jupiter?
There might be, if he's got really good radiation. All right, this is the radio Joe set up. It uses a couple of wire antennas that are crossed and a small radio here. Now, Astronomical League. Anybody here belong to Astronomical League? Okay. They have what they call observing clubs. About 2 years ago, they started an observing club for radio astronomy. Basically, it's a set of steps you go through, and as you pass and complete any of their requirements, then you are given a certificate of proficiency in that particular area. Radio astronomy actually has 3. They typically go like Olympics, bronze, silver, and gold. I'm putting together my paperwork now to get the bronze one for the work that I've been doing at 1420. So, what do you have to do this? Remember I said I just need a little dongle RTL SDR radio, right? Okay, well, you have to have some sort of a dish. Just like you have to have a lens or a mirror in visual astronomy. And then that radio stuff is focused, waves are focused up here to what we call the LNA, low noise amplifier. Low noise is very critical because these signals are very, very weak. And we typically also will put a filter in there, so we're only amplifying stuff in the region we want to see. So this is an RTL SDR. You can buy them on Amazon for 25 bucks. This is the amplifier filter combination that I built. It uses amplifiers from a company called Mini Circuits. Whoops, sorry. It has 3, I think they're 15 dB amplifiers. So that's a total of 45 dB of gain. Everything in radio astronomy is rated in dB. Okay, so that's another whole language you have to learn, another whole set of math. It's not that hard once you get the concept. Right here is a filter that goes from 1350 megahertz to 1450. Well, my 1420 is right in the middle of that. So anything outside that range is going to be knocked down and won't be amplified. This is the input, goes through here, amplified twice more, and then it goes through a coaxial cable down to my RTL SDR. There's the whole thing set up. The can is an old paint can I took the cover off of. There's a little wire sticking down inside here that's 1/4 wavelength at 1420. And then the coax brings that around. I don't have the RTL SDR on here. All right, so that's the dish I started out with. That's a friend of mine up at, there's 2 or 3 different places to do astronomy up in Dade City. There's one called Farr Observatory. Farr Observatory. It's an acre of land 3 miles south of Withlacoochee. A friend of mine who actually now owns the place. Anyway, we got this 10-foot dish, and I used to say I wash dishes. Okay, so I didn't like the fact that it was so dirty. Now you can see it's not perfectly configured. It's slightly bent, but you know what? I had a guy bring it to my house on a truck for 125 bucks. I was happy. Okay, so we had to figure out how to put it in the ground. Well, the last people just took the pole it was on and cut it off at the ground. Well, I thought about trying to get something welded on here to extend it down. That ended up being a major project and very expensive. So I said, all right, we had a bunch of old 4x6 PT beams laying around. So we got some all thread, put them through there, drilled it through, bolted them to the side, and stuck the whole thing in the ground. Okay. Now, fortunately, this one I have has a motor on it. And I'll show you why that's important in just a moment. Now, that's what we call a Four-Bands inclinometer. All right? Magnetic level, put it on there, and I know how the dish is tilted. And that becomes important because, well, we'll show you that in a minute. Now, some of the software we use basically looks like this. It's a radio receiver. If there were a signal here, it would show modulation. There's 2 or 3 different types of software. This one's called Radio Sky. It's very popular.
Was that just a C-band antenna you were working with? Classic old school satellite dish before.
The dish was, yes, but the receiver part is what I built.
Yeah, I understand.
Right, yeah, just go find one, and
Yes.
tell the guy you want it, and they'll probably be glad to have you take it out of their yard.
I took one out of my yard 20 years ago.
Well, there you go. There's a lot of them around. I drive around, and I say, oh geez, there's one there, I need to get that one. Okay, drift scan, what are we looking at? Can you bring up your program?
But the dish don't.
Unless you really have a lot of money, or a
We have one. You want some?
a German equatorial mount big enough to move about a 40-pound, 100-pound dish. You can't track, okay? We can't track as amateurs. Now, the GBT tracks, okay? Yes, it's the largest movable object on land in the world, weighs 17 tons, and it tracks, okay? To great accuracy. I can't afford that. So what do? We bring up a program that he's going to do right now, and first thing you do is you get your dish pointed as close to the meridian south as you can. You can pick another, but it's not wise, and I'll show you why in just a second. Because most astronomy programs will give you a meridian, which of course is the north-south line. And as we know, since we're in the northern hemisphere, stuff goes like that. If you're looking north, it's hard to, it goes like this. Okay? There we go. All right. Now, let's see if you can get a meridian on there. That's probably, well, now can you make it a little bit later at night so we see some stars?
Is this free or does this cost money to get the software?
This program?
Radio Sky? Is that what you're doing?
Oh, no, this program is Redshift.
Got it, okay.
This is just astronomy software.
Okay.
Okay, so let's presume that we have, can you click on this dot right here? To give us information? Okay, yes, that's exactly what I want. So, let's say that I want to do a radio, that's a target that I want to see with my radio telescope, okay? A star would never be, but let's say that's, Cygnus A. Okay, so I set my clock up to be 5 minutes before when I want to observe. And I get the readings, okay? I have altitude and azimuth. This says 190, typically it would say 180 if everything was set up right. And it has the altitude. Okay, so now remember my little poor man's inclinometer? I can move the motor until my dish is pointed up at 37.05 degrees, okay? So, 5 minutes before this is supposed to cross that line, I start my radio. And if I'm really lucky, and if everything works, that'll cross that line, my telescope will detect it, and I let it run for 5 more minutes just to be sure, and then it shuts down. That's drift scanning. It's the same thing you would do with a Dob if you just wanted to watch something pass in front of your field of view and didn't want to track it. Okay, so that's essentially what we do. Okay, put my slide back up. All right, that's all right. Okay, that's with everything set up. My inclinometer The software that we use, there's something called SDR Sharp, Radio Sky, 2 or 3 other things. Drift Scan, okay, that's where we were. So, what's next? Well, being involved with this, I got involved with a guy who had access to I gotta make sure I say this right, 30-meter dish, okay? I wash dishes, remember? So I'm inside the 30-meter dish cleaning it up, had not been used in a long time. This was the LNA horn that came with a professional setup that we bought. There's a company in Texas called Radio Astronomy Supply, and they sell a radio called the Spectra Cyber, which is the top of the line for amateurs, and it only reads at 1420. Significant number, 1420. That's when we were using it, okay? We actually had access to this old NASA camera tracking dome back here, and we set up our equipment inside of it, and I thought I had another. Nope, I didn't. All right, that's all I had. So we were able to sit inside and have our radios running, do the plots. I've got gigahertz worth of plots that we've analyzed, all different things that we've looked at. I enjoy radio astronomy because it's different. When you talk to your friends about astronomy, how many times do their eyes glaze over? Anybody ever had people their eyes glaze? Well, guess what happens when I talk about radio astronomy? Your eyes glaze over, okay? And that's cool to me. I love it. All right. So, I have brochures here on a Society of Radio Amateur Astronomers. If you're interested, how else may I answer your question?